continue our discussion on transistors, and now we take the important aspect of a transistor circuit, that is biasing a transistor. Now, first thing is, let us answer a very pertinent and important question, that why do we need biasing? And then how do we bias? I am sure you understand the meaning of biasing. Biasing is that the two junctions of a transistor, the emitter junction and collector junction, have to be provided with a DC potential, a DC bias. So, that is known as biasing. And the question, why do we need to bias a transistor? Because we want the transistor to remain in active region. You will recall that the IV characteristics of the transistor, we divided those collector characteristics into three divisions: the saturation region, the cutoff region and the active region. The transistor has to be operated in the active region when it is being used as an amplifier. So, that is why we need the biasing of a transistor, that means biasing of junctions. And remember, for an transistor to work as an amplifier, the emitter junction has to be forward biased and the collector junction the reverse bias. Now, how do we bias a transistor? So, we are going to talk about various schemes of biasing and relative advantages and disadvantages of each scheme. But before that, because this will need the concept of load line and operating point. First, we talk on these points: what is load line and what is operating point, that we should discuss. For this, we consider a small circuit. Let us consider this circuit and apply Kirchhoff's voltage law to the collector circuit. Then we will see that we can write VCC equal to RC into IC and this voltage VCE. So, we get VCC equal to IC RC plus VCE. Now, here RC is constant, VCC, this is the battery which is also constant, but when we superimpose the AC signal on this amplifier like this, a coupling capacitor, and here is the AC source, and this source may be anything, for example signal from a mic if it is a audio frequency amplifier, or some other radio signal if it is a radio frequency amplifier. So, this is the AC signal. When this is superimposed over this DC, then these currents and voltages will vary. So, this is variable and this is variable. These two are the variables, these two are constants, and we rearrange this equation and we get, let us call this as equation 1, and if we rearrange it, we get I C is equal to minus V C E by R C plus V C C by R C. Now, this is the equation of a straight line, and we can compare it with the standard equation. You must be familiar, y is equal to mx plus c. This is the equation of a straight line, and this gives the slope of the line, and this is the intercept on the axis. So, this is the equation of a straight line, and you know how to plot the straight line. Here on this axis, when IC, this is IC and this is VCE. When IC is 0, then when IC is 0 here, then this will give that a cut, that VCE is equal to VCC. This is when IC is 0. So, this gives this point, and similarly here VCE is 0, and that will give this point, which is the maximum current IC maximum, and this is equal to VCC by RC, and then we connect these 2 points, and this is VCC, the battery which we are using to reverse bias the collector. Now, this is called that the slope of this line is minus 1 by RC. Slope of this line is minus 1 by RC. This becomes a useful line when we draw it over the output characteristics of the transistor like this. This is IB equal to 0, IB is increasing this way, and for example, this is 20 microampere, 40, 60, 80 and 100. This is IC, and you will remember that this is the saturation region, this is the cutoff region, and here is the active region. Now, this load line, when it is drawn over this was the point VCC, and this is maximum collector current C max, IC max, which is equal to VCC over RC. So, this is the load line. Now, we choose a operating point, and that operating point is also known as Q point. Operating or same as Q point, quotient point, Q point. By choosing a operating point, we mean, for example, this point is our operating point Q. Then that means we have chosen a DC collector current which will be flowing in the circuit in the absence of AC signal, and similarly, so this is called actually ICQ, that means collector current at Q point, and similarly this is called VCEQ. These are the Q point values, quotient point values for the collector current and the voltage drop across the transistor, the collector and emitter junction, that is VCEQ. Now, when we apply the AC signal, then the currents and voltages will vary. For example, here this is the applied signal. This is the applied signal and the output current will vary accordingly, and this shows that, for example, from the ICQ value it will go less and on the higher side, and similarly the current, lower part of the current will be here, this is ICQ, and then it will go to the higher side. So, currents and voltages, the IC, the collector current will vary, and the voltage VCE, IC and VCE, they both will vary across the Q point. So, I am sure now it is clear what is Q point. Q point is choosing the appropriate values of the DC collector current in the circuit, and that will give a DC voltage drop VCEQ, and the current and voltages, this voltage and this current will vary according to the input signal, and for simplicity we take that AC signal is sinusoidal in nature. Now, this Q point, the operating point may shift, and I will tell you what are the reasons for the shift, and we have to choose the operating point properly. If shifts and if it is closer to the saturation region, then distortion, output will be distorted. We expect from a amplifying circuit that output signal should be exact replica of the input, and only the magnitude will vary. This magnitude here, it is in current form, and we will see later that this enhanced current will give the voltage, a higher voltage signal also. So, and if this shifts towards the cutoff region, again there will be distortion, that I will make clear. Let me first write that why Q point should vary. The Q point may shift because of temperature change. Temperature change. I have talked about this point, how the temperature changes. The temperature changes from season to season, it changes from place to place. For example, in Himachal and in Delhi there may be a difference of 30, 40, 50 degrees, and also it changes because of the ambient of the circuit. So, temperature change. Now, what are the parameters of transistor which are temperature sensitive? We have talked about the reverse saturation current. This is temperature sensitive because it arises because of the thermally generated charge carriers. If temperature falls, this will be less. If temperature rises, this will be high. Similarly, beta, the current gain, you remember that I showed a graph that it varies with temperature. With rise in temperature, it increases, beta increases, current gain increases, and with fall of temperature, it falls. And the third quantity which is temperature sensitive is VE, that is this drop, this voltage plus minus, this is VE. This is also temperature sensitive, and we have talked about the degree of variation with temperature of all these three parameters. So, this is one cause. What is the other? The other two causes are aging. That means, continuous use of the device for long period may change its characteristics, and these characteristics, if the biasing circuit is not properly fabricated, then this will result in changes in the signal output, for example. And the third and last point about this is changing device with, say, different current gain beta. Why we change the device? As you must have seen, in discrete circuits, sometimes due to overheating or some bad handling, the transistor may be damaged, and that needs to be replaced by another transistor. Now, there is a wide variation of current gain beta in the same lot, same number of transistors. If you look at the manual of the manufacturers, then actually they give a range of this beta instead of giving a single value. So, this may change the characteristics if the biasing network has not been designed properly. Now, so Q point may shift, and I can show this shift like this. Earlier we start Q here, but it may shift, for example, here, and when we apply the AC signal, then it will not, because the portion of the wave which appears in the saturation region, that is the region in which the output current does not vary according to the input. So, in spite of the fact that our input was a pure sinusoidal signal, the output may be like that, distorted. This will happen when, for example, we replace the transistor with higher beta, or temperature changes, it becomes higher, then this will happen. While if beta is less, then it will change in the other direction. If this was our original Q and if it shifts here and this is the cutoff region, and when we apply the signal, then the output will be distorted, and because beyond it, it will be independent of the AC signal. So, it will be distorted like this here. It should be like this, but this portion will be missing. So, we will get a distorted output. So, that means the two things, that we start with the right choice, and right choice is somewhere in the center, not exactly in the center, but if it is here and here, then this is good enough. The choice becomes more stringent when we talk of power amplifiers where the swings will be very large. At the moment, we are talking of small signal amplifiers, small signal amplifiers. So, the Q point has to be chosen properly. We talked about the variation of the Q point, and in this connection actually we define a stability factor. Stability factor for a circuit, and this is denoted as S. S denotes stability factor. Now, this is defined for various variations. For example, delta IC over delta ICBO. That means change in the collector current, because this is temperature sensitive, changes in the reverse saturation current. We can say another stability factor, which is IC with change in beta, the current gain. If current gain changes for any of the reasons stated above, then the collector current will change. Or yet another stability factor, which is delta IC by changes in VE, because you remember that IC is beta IB and beta times ICBO. So, if ICBO, the reverse saturation current in common base, if it varies, it is multiplied by beta for common emitter circuit, and this becomes a significant variation. Similarly, beta changes, then the current may change, and if this voltage changes, that will also change the current. Now, one thing very important, that we have stated various reasons for the variation, but this is a very important statement, that a circuit, if it shows stability against one kind of variation, then it will take care of variations due to other causes as well. I repeat that the cause of variation is immaterial. If we have taken in the design of the biasing circuit, if we have taken into account variation of any of these three parameters, S, S prime, S double prime, this is three reasons, and so if we have designed the circuit to take account of any one kind of variation, then the circuit is supposed to remain stable. By stable we mean that the Q point will not shift significantly if the temperature changes, aging, or whatever the causes we have stated. So, remember that stability in stability the cause of variation is immaterial. The circuit has to be designed to take into account this stability. That means, circuit should be stable, Q point should remain stable. And so, how we, this is by fundamental definition of stability, but we can find one expression also for stability. If we, for example, differentiate this equation, if we differentiate with respect to current, that means differentiating with respect to IC this equation, then we will get 1 beta dIB over dIC plus beta dICBO by dIC. Now, this is equal to this term, this is equal to 1 by S here, this is equal to 1 by S. So, we can write this in this form: S, the stability factor, is equal to beta divided by 1 minus beta dIB by delta IC. Now, stability factor may vary, the smallest value possible is 1 and higher may be say 50, 100 or so. This is ideally stable, this is very unstable. So, the value of S around 10 is good, this is a stable circuit. And there will not be any significant change in characteristics if the parameters of the circuit vary, because any of the causes which are mentioned above. So, what does it basically speak? That in all circuits, when collector junction is reverse bias and emitter junction is forward bias, then the output current will be a function of the input current. But here this says differently, that input current should be made a function of the output current. When this happens, then we can achieve stability. I will explain this point further, and this is achieved by using negative feedback. So, IC we are supposed to maintain constant, and it should be made independent of the variations of temperature, aging and replacement of devices, and this is achieved by making circuits which will take account, they will include negative feedback. We will explain this, that how the circuit we will design and how will it work. First, let us see what is called a fixed bias. Fixed bias, we will see that IB, the input current, is not the function of the output current IC. Reverse is always true, of course, as long as we have biased the collector in the reverse bias and the emitter in the forward bias, the output current will be a function of this, but definitely in the fixed bias the input current will not be a function of output current. the circuit. Let us look at the circuit. This circuit, this is drawn here in the most primitive way. This is not the actual way the circuits are drawn. This needs two batteries, but we can see that even single battery can be used to bias both junctions. So, this circuit, you see here that the negative terminal of both the batteries is grounded, and this is connected to the base resistance. Similarly, this is connected, positive is connected to the collector resistance. So, assuming and believing that the other terminal of the battery is grounded, this circuit can be drawn like this. Here this is plus VBB, this battery, and this is plus VCC, this is RC, and this is RB, and we can write down the expression for the input current. This is plus minus VBE, and this will be very simple. As it is here, we can write that IB, the current which will be flowing here, IB in this circuit is VBB minus VBE divided by RB. This will be, but again we further modified. Here still there are two batteries, but let us see this circuit. This circuit, the only difference is between the two, that here VBB is equal to VCC. So, this is the way circuits are drawn. For input side, we can make a circuit like this where VBB is equal to VCC, and on the output side we can make a circuit if some calculations have to be made. And here now IB will be equal to VCC, because VBB is equal to VCC minus VBE divided by RB. This is 5, 10, 15 volts. This voltage is very small. So, in many situations this can be neglected, and then this IB will be approximately, very closely actually, equal to VCC by RB. So, this is IB is fixed, is constant, while we have seen that the stability requires that IB should be a function of IC, which is not here. That is why it is called fixed bias. And so, this variation term is 0. So, if we put it this in 0 for a fixed bias, stability factor is equal to beta. If this is 0, then S is equal to beta, and beta is high. This is definitely for all practical transistors, beta is higher than 50, and normally 100 200 and so on. So, this is highly unstable circuit. I have mentioned here that for stability this factor S should be around 10, but equal to beta is very high. So, remember one thing, that fixed bias is almost never used in transistor circuits, though it is simplest and the design is simple and the calculation is simple, but it is never used. The reason is that the circuit will show high instability. The Q point will shift as the temperature goes up or you replace one device with the other. So, what are the practical circuits which are used, and that we will be considering. Practical biasing circuits, there are practical biasing circuit, and there are three circuits. One is what we call self bias. Self bias, which is also called emitter resistance wire, emitter resistance bias. This self bias, this is also called actually base bias. One and the same thing, self bias or base bias or emitter resistance bias, one and the same thing. So, in this self bias, this is highly stable, circuit is highly stable and most widely used. Most widely used to bias a BJT circuit. And second is emitter bias. This shows stability as high as for self bias. The stability is as high as in case 1, the self bias, but it needs dual power supply. Dual power supply. Let me explain what is the meaning of dual power supply. Two voltages with respect to ground, this is ground and this is plus VCC and this is minus VEE. These two voltages with respect to ground, the power supply should be able to provide. For example, a plus 12 voltage and minus 12 voltage should be available, and both with respect to ground. If we take single battery and we connect this point and this point, then this is only one battery. This may give either a negative voltage and or a positive voltage, but both voltages cannot be obtained from a single battery. Of course, we can design to provide two voltages with respect to ground. So, this is called dual power supply. Now, emitter bias, while it shows stability as high as in the self bias, but it needs a dual power supply. This is also very popular biasing scheme. Almost all operational amplifiers, op amps, they make use of this scheme. So, very important. And the third one is collector feedback bias. Collector feedback bias. Here the stability is reasonable, shows or exhibits reasonable stability, but not as stable as other two schemes or arrangements or circuits. But this is very simple circuit, as we will see, makes use of fewer resistances, and if stability is not the prime criteria, then this is very widely used, because there are many situations where little bit variation of the Q point, that means with reasonable stability we can work the circuits. So, there collector feedback bias is used. So, these are the three practical circuits which are used: self bias, emitter bias and collector feedback bias. We will discuss one by one these schemes. So, let us first talk the self bias. In this biasing scheme, one resistance which we call Re, it is attached with the collector. You will see that in the fixed bias there was no resistance connected to the emitter, but in this scheme a resistance Re is connected. So, the circuit becomes this. These are the currents. The IB will flow here, IC, and this is IE. Now, if this resistance is removed and directly if emitter is connected, then we come back to what is called fixed bias. This is the self bias, because inclusion of this resistance. Now, this will be the part of the input circuit, and I will just show you that how the input current finally what is going on in the transistor base lead here, that will be dependent on the collector current. So, let me redraw just for the input case. I draw this circuit and this is this. This is the circuit for the input side, and we apply Kirchhoff's voltage law. voltage law, which is nothing, simply the summation of voltages. So, we can write that VCC will be equal to the voltage drop here, this voltage drop, and this current will have a voltage drop here. So, the Kirchhoff's voltage law results in KBL to the input loop gives IB RB plus VBE plus IE RE equal to VCC. You will remember a very fundamental thing which we talked earlier, that in a bipolar transistor, when the emitter junction is forward biased and collector junction is reverse biased, in that case the emitter current and collector current are almost same. This we make use here. So, this becomes IB, then we write from here IB, the expression for IB is IB equal to VCC minus VBE minus IC RC IE RE divided by RB. And as I said earlier, that this voltage is comparatively a much smaller to other voltages, this or that. This is around 0.7 volts, VBE is 0.7 volts for a silicon transistor, and this is 0.3 volts for a germanium transistor. So, this we can drop to make some simplifications, and important salient features remain intact. So, this is VCC minus IC RE by RB. This is the base current. Now, we can see the difference between the fixed bias and in this self bias case. Here the input current, remember input current is a function of output current, and this has been possible because of the negative feedback which is introduced in the circuit because of this resistance. If we make RE equal to 0, then this is fixed bias VCC by RB. Now, this is the negative feedback, and that takes corrective measures. How? Let us look at this. For any reason, the collector current goes high, then this term will be less, and obviously IB will fall down. So, the rise in IC will be checked by fall down in IB. You will remember these output characteristics. This is IC, this is VCE, and here is IB. If IB falls, then there will be less collector current in the circuit. So, this is the corrective measure, that if it falls, then this term will acquire higher magnitude and the current, input current will increase, and that will again take care of the fall in current, it will enhance the current. So, in a nutshell, we can say that this circuit takes into account of the variations which are bound to occur because of the reasons which were specified earlier, and it will maintain the operational point, the Q point, very close to where we have chosen. So, this is we can further explain this, and this equation which we wrote, I b R b plus V b e plus I e, which is same as I c R e, is V c c. Now, we make use of the thing that beta is simply equal to I c by I b, and I e is equal to I c. So, then this equation becomes I c by beta R b plus I e, again I c, because I c and I e are the same. This is equal to V c c minus V b e, or from here we can write I c equal to V c c V b e by R e plus R b by beta. Now, if we design a circuit where R e is much greater than R b by beta, then this becomes of much smaller magnitude as compared to this. So, our expression for the collector current is all becomes independent of variations in beta, and this is V c c V b e by R e. So, the collector current becomes independent of beta, and as I made a very important statement earlier, I repeat that if this circuit works perfectly all right, it takes into account the variations in the beta, then it will also take account of the other causes of variation. The cause of variation is immaterial. So, this is highly stable circuit, and here I c is not the function of the current gain beta, which shows very high stability, and this is achieved because of the negative feedback through the emitter resistance. There is a variation of this circuit which is often used, and that variation is called voltage divider circuit, self bias, but with little modification. That is the one which is most widely used, and we will talk about that in the next lecture and continue about other circuits of biasing.